So my name is Sven. I'm a software developer at DATEV, and today I would like to talk about our journey of accelerating our seed generator. So I would like to share some experiences and lessons we learned. I work in the tax department, so my team and I are working on a calculation DSL in the tax domain, of course. So our subject matter experts are using our DSLs to express the German tax law. So here on the right side, you can see a small example of one of our DSLs. And as the title of the talk states, our major generation target is C. So we generate C files, and we also have a Visual Studio project generator. So that Visual Studio project is used to compile and link in DLL, which is then loaded into our legacy on-premise application. So this is basically an old UI application we have, and we can exchange. Okay, so our major generation target is C, but as Marco said yesterday, everything is moving into the cloud. So we also have a team working on a cloud application, which is not developed in MPS, but we are planning to have a Java generator soon. So our DSL is quite mature already and it's feature complete. So we have around 30 in-house subject matter experts working with those DSL on around 13 tax products. And we had 2 releases last year used in around 80,000 offices. And this year we are planning to have 4 more releases. Or we already had 2 other releases this year, and we are planning to have 2 more releases of that DSL, which is shipped with the on-premise tax application to our customers. So yeah, let's dive into our C generator. So we have a couple of C generators, and as I already said, we have a Visual Studio project generator, which we developed, and we use 3 external generator bundles. So the main bundle we use is mbeddr-C. So we transform our tax DSL to mbeddr-C, and then mbeddr-C will generate C files. And our DSL also embeds kernel F expressions. So I hope you know kernel F. It's quite nice to do fast prototyping because it's a rich expression language. And we have a closed source kernel F2C library developed by itemis to transform kernel F expressions to mbeddr-C. And for interpreter test and entry points in the pipeline, we also use various base language interpreters. So here in this small sketch, you can see all the parts involved in our generation process. So we have our user model, and then a couple of transient models, of course, generated files I already mentioned. And the final output is the compiled DLL, which we would like to have at the end. And actually creating that DSL took around 25 minutes. We also can generate an executable for unit test, but this took around 50 minutes. So our users like to use the interpreter, which is written in Java, instead of the C files. Obviously, so our users can use the interpreter to execute unit tests, but for system and integration tests, our users would like to have this DLL to test it together with this on-premise application I've shown before. And obviously, waiting 25 minutes every time to have a new DLL to do some system testing is just not an option. So we received the goal: when the model is changed slightly, the DLL should be created within 13 seconds. So that was the goal, which was defined by our management. But if we consider that linking all generated object files together and linking already costs 15 seconds and there's not much we can optimize, the goal is actually when the model is changed slightly, code should be generated within 15 seconds. So that was our goal, to decrease the generation time from half an hour to 15 seconds. And you might think maybe we should have changed the technology. We actually were considering that, using Xtext, for example, instead of MPS generators. However, our generator was already quite feature-rich, and we had new features which we had to implement, and also the generator had to support those features. So it was just basically no option that one part of our team is basically re-implementing the generator from scratch in another technology, and the other part of the team is maintaining the old generator. And we also had upcoming releases last year. So we decided that we will go for an iterative approach and try to optimize the generator step by step instead of switching technologies or rewriting everything from the scratch. Okay, before I start presenting some improvements we did, I would like to tell you how we discovered bottlenecks. So we use two options. The first one is the model generation performance report, which is a built-in feature in MPS. So in the settings, you may know you can switch on the generator performance report. You have 3 different levels of details, and if it's switched on, you will receive more messages in the make view, which is really easy to set up. The overhead is quite small, and the nice thing is that the times are sorted. And in MPS 2021.2, they introduced even more details, so there are even more messages written. However, you may know that this view is limited to 10,000 messages. Yes, there's a settings button, so you can increase the limit from 10,000 on our machine. Maybe 50,000 also works, but you can't increase the limit to 100,000. And already tiny models create 3,000, 4,000 messages. So I guess our biggest user model will create something like 100,000 messages. So this model performance report was not really an option to analyze details. So the second thing we used is JVM profiling. So we used the UKIT Java profiler in the beginning, and now we are using IntelliJ Ultimate. It's also really easy to set up, and the overhead is quite small. But compared to the model generation performance report, you will receive more details, which might be overwhelming in the beginning. But once you are used to it, it's really nice to have this level of details, and you have different views and another nice options like jump to source code. You can analyze the source code and so on. However, those tools are paid. So it's up to you to pay for those versions. I don't know if there's like any free, really good JVM profiler. Okay, using those techniques, it was clear to us that our major bottlenecks is resolving dynamic references, and this is the first part I would like to talk about. So what's a dynamic reference? We speak about a dynamic reference in the case of a reference macro. Actually, now, let me try to use the pointer. Like this, right? Okay. Okay, I won't use the pointer, that's so complicated. So let's just point. So we speak about a dynamic reference if a reference macro like that returns a string. So there's a small example. And resolving that string is really expensive in MPS because MPS tries to find a node in your model that is of the same type, and has the same name. And in order to find that node, MPS needs to construct a scope. Obviously, MPS don't want to take any node in your model that is placed somewhere and has the same name. So it constructs the same scope to find the exact node. And constructing that scope is very computation intensive. So if you have a lot of those dynamic references, and we had 150, you will waste a lot of time or spend a lot of time with computations. So on the other hand, we have static references, or in the model generation reports, those are called regular references. Static references are reference macros when a node pointer or a node is returned. And this is really fast. We usually do this with using mapping labels. It's not really working, isn't it? Okay. Okay, so usually you use mapping labels and then you can return nodes, and this is really fast. So here you can see one example of a model generation report of our biggest user model in June 2002. And there you can see that resolving the references took 14 minutes of 90 minutes generation time. So we spent around 70% of the time to resolve those dynamic references, and it's clear that this time we have to reduce. So over the last 12, 13 months, we basically took three main actions. The first one is really simple. We replaced a lot of dynamic references using mapping labels, which was possible for some cases and really easy for some cases. And we already saved 4 minutes. So we basically reduced the time resolving those dynamic references from 14 to 10 minutes. The second bigger actions we did in the beginning of this year is that we moved from MPS 21.1 to MPS 21.3. And in MPS 21.2, JetBrains did a nice thing. They optimized reference scopes. So in 21.2, scopes are cached. And if you have multiple reference macros using the same scope, then you only have to calculate the scope once. And this surprisingly reduced our generation time from 19 to 9 minutes. So we saved just 10 minutes by moving to a new MPS version. The not so fun fact about this topic is that MPS 21.2 was released in October 21, and it took us around 1.5 years to migrate to that new version. And the issue why we had to wait so long is that it took some time until mbeddr-C, ETS3, open source, and MPS extensions were migrated to that new version. So here in this round, I really would like to motivate the community and all customers using those products and ETMIS and JetBrains to maybe accelerate this processing of migrating those libraries to a new version so that we can try out new MPS versions later, because obviously there can be a major benefit from that. The third action we took, which is somehow questionable, is that we replaced references by plain text. So we still had some reference macros returning strings left, and those were actually still really slow. So we are still spent around 4 minutes resolving dynamic references. And there were some cases where we looked at the code and we couldn't really figure out how to use mapping labels in that. Actually, when I was preparing this talk, I realized that there is actually a way, but we have to do some major changes to our generator. And there is still one case where I don't know how to use mapping labels in that. So instead of changing our generator or still wasting time with resolving dynamic references, we decided to introduce plain text concepts, I call it. So instead of having a reference and a reference macro, we have a plain text concept that just has a name, and the generator will then just create plain text. So this saved us another 3 minutes. But of course, the maintainability of those plain text concepts is really bad, so I don't really recommend it, but we save a lot of time now. Yes, Marcus. Okay.
Was this something you had to change in mbeddr? Because I assume that some of the mbeddr-C were also slow.
So the question is, if we had to change something in mbeddr, we basically introduced an mbeddr extension language with plain text concepts. So there are arbitrary text concepts in mbeddr, but they didn't really fit our purposes in all cases, and also the editor are not looking so nice, so we decided to introduce our own concepts. Okay, after those 3 actions, we basically removed all dynamic references. And now I would like to talk about the next topic, which are scripts without any value. So I already said that we use mbeddr-C, and mbeddr-C is a quite complex framework of many generators and many scripts, and it can do a lot of stuff. So like you can use older C concepts, or you can transform the model to older C language and so on. And there is one major script, which was a major bottleneck, which is sorts the content of a root file, which is really nice if you're a mbeddr user, so you don't need to care about the order of types. So you may know in C you need to declare a type before you start using it. And in mbeddr-C, you don't need to take care of the order because you have a post-processing script that sorts the order afterwards. However, as I already explained, we transform our tax DSL to mbeddr-C. and we create mbeddr-C root nodes with thousands of entries. And sorting those thousands of entries took around 1 minute in our biggest user model. And we thought, okay, this minute is just wasted because the generator is usually written once, but executed countless times. So why actually should we sort the content every time? We as generator developers could ensure that the order is always correct so that we don't need that post-processing script. So sorting is currently, or was hardwired to mbeddr-C. So we requested a new annotation, which was implemented by itemis. And now you can add the skip content sorting annotation to your root node. And if you do so, the content is not sorted and you save some time. And actually the fun fact is that we didn't need to change anything. Everything was already in the correct order, which was really nice. So this was last year. This year, we analyzed all scripts from mbeddr again, and then we figured out that there are some more scripts checking if something should be transformed, but then they realized that there is nothing to transform, so they spent seconds with just checking something, but actually they don't have any value for us. So we actually removed even more scripts than the sorting content script. Yeah, now next bigger topic, generator priorities versus generation plans. I already said that we have multiple generator involved, and there are basically 3 ways to define the order of generators in MPS. So actually there are 2 ways, and there is one way where you just don't define the order, and then there is an generation plan algorithm in MPS, which will then on any heuristic try to guess the correct order of generators and execute them in that right order. Of course, this is not always a good case. So sometimes you have to define the order or to tell MPS which generator shall be executed before or after another generator. So for that, you can usually use generator priorities, and this was also the option we used. It's the first step. So in the generator priorities dialog, you can define rules to tell MPS which generator should be executed before or after another generator. And if you do so, MPS will collect all generators, try to calculate the correct order, and then apply all generators to the generation process. The drawback of that is that you don't have an option, at least we don't know an option, to exclude generators. So all generators which are applicable to your model are applied. And this actually had 2 issues on our side. So the automatically calculated generation plan included 53 generation steps, because there are a lot of mbeddr and a lot of base language generators. And we realized that actually 35 of those generation steps are passive. What do I mean with passive? The output is exactly as the input, so those generation steps are doing nothing again. And checking the model performance report, you can see that those passive steps takes around 600 milliseconds to 2 seconds in our case. And if we sum up those 35 steps, we will count around 40 seconds we waste just for executing those passive generators. And the second drawback of not excluding unwanted generators is that we always generate Java files. And of course, if we only want to have an DLL, we don't need Java files. We only need Java files to execute the interpreter test using that MPS1 action or on CI/CD. So generating and compiling Java files also takes 90 seconds. We would like to remove from our generation process. And what you can do is you can switch to the tax, to the generation plan DSL instead of generator priorities. And this is what we did. So this is really nice. Instead of having 53 generation steps, we only have 9 generation steps now, and we could easily remove all mbeddr-C, kernel F2C, and base language generators we don't need. And this saved us around 3 minutes. And also we developer like it because now the transient models, the generation process is easier to understand and easier to debug because you only have 9 transient models instead of 53 transient models. However, the generation plan DSL is not perfect. So there are various issues. And the 2 major issues we have are is a spurious error message called model use language blah blah blah. So it means that we use a DSL that has a generator, but we don't use this generator in our generation plan because our own generator already transforms those nodes and keeps care of those nodes. But to satisfy the model checker and avoid this error message, which you can't suppress, unfortunately, because it's not executed on the fly in the editor, we have to add an additional transformation step at the end, calling those 5 generators, which again takes time because we have passive generators in our generation toolchain. And the second issue is that we don't want to execute the Java generators every time. So the first step, we had to fork to our interpreter gen plan. But as I said, generating Java files took around 90 seconds. So we wanted to have some checking conditions, checking global flags if the Java generator shall be executed or not. And this is not possible with the generation plan DSL. You might think it's in DSL, so we can add new concepts to DSL and maybe extend the generation plan DSL. Yes, you can extend the DSL, but the interpreter interpreting that DSL or that generation plan is fixed. So you can't extend the interpreter, unfortunately, because there's no API for that. So what we thought is, okay, let's don't use the generation plan DSL. We will just write our generation plan in base language. And this is possible. What you have to do for that is you have to add and face it to your generation plan. And so you have to add and face it that once after the configure step and before the generate step. And then you have to assign to this custom plan in generator, basically an empty generator, because before it's null, this flag is not documented. So we don't know if we actually are doing a hack here. JetBrains, please never remove this custom plan field. Otherwise, the workaround will never work. And once you assigned an empty generator to that, you can basically inject your own generator with this generation option custom plan. So if you do so, you can write your generation plan in base language. There you can check any condition you like, any global flag you like, and yet you're just injecting your generation plan. And also we prefer to write our generation plan in base language than using this generation plan DSL. The second solution would be to avoid the Java generator at all, and this is something which is currently ongoing. So the first thing where we need, or where we needed the Java generator was this run action. So you may know this complicated run dialog, which is not really nice for subject matter experts because there are way too many informations. So we developed our own interpreter run view, which just calls the interpreter directly without the need of generating any Java files. And the second step, which is still planned, is that we have to call the interpreter on CI/CD, and we need to develop an entry point set, which we haven't done yet. Once this is done, we can remove the Java generator at all, and also our faceit workaround. Okay, 5 minutes left, so I have to hurry up. What's really nice is the next step we did was multi-threading. So you may know there's a generate in parallel option in MPS. So you can generate models or transform multiple routes in parallel. And until 2 months, our generator was not able to be executed multi-threaded. So there were a couple of issues we fixed lately. Also in mbeddr-C, there was one issue we had to fix. And once those issues were fixed, we reduced the generation time from 3 minutes to 90 seconds. So I really would encourage to try out the generate in parallel option. It's really nice. However, what you have to keep in mind, what we figured out is that type system calls, so if you use the .type operation in the generator, those type system calls are synchronized using a lock. So this actually slows down the generator if you have those type system calls in reduction rules. Even a multi-threaded generator is slower than a single-threaded generator if you calculate types in reduction rules. So what we do, and what we already did before, is that we pre-calculate all required types in mapping scripts. However, you have to consider that mapping scripts are executed sequentially and applied to the complete models. So all mapping scripts are executed in a single thread, and you don't have any multi-threading advantages there. So yeah. So it's also nice to avoid mapping scripts and to use reduction rules instead, but don't calculate types in reduction rules. Okay, I will skip this slide. It's mostly about CPU speed matters. Our users have to use a weaker CPU, so we were quite surprised that the generation takes 90 seconds on our machine and 145 seconds on our user machines. But we are about to solve this issue and also provide stronger CPUs to our users. So last topic, I will go briefly, is that what I didn't mention yet is that the initial approach of our generator was to always generate everything. So what our generator does is that it collects all user models, also external models from other projects, combines them in one model using a pre-processing script, and then generating code from that combined models. This has a couple of advantages. For instance, you can optimize the model because you always know everything, and we can generate cross-model files. However, the drawback of that is that it's now quite complicated to have single model generation. Of course, it doesn't make sense to always generate everything. If only one node of, I think, 300,000 nodes is the size of our biggest user model. So if only one node of 300,000 nodes changed, you only want to regenerate this one node or maybe the stuff around that one node, and you don't want to regenerate everything. So what's currently ongoing is that we would like to move to single model generation and only regenerate the changed model. However, the advantages of this combined model generation, I call it, are now handicaps to redesign the generator because we have to change a lot. So we basically have to re-implement our generator. And we estimated effort of 2 to 3 months. So maybe it will take another month until this work is finished. And yeah, in the past, we decided that we can't do the single model generation earlier because we have to implement other features. But now all the other features are implemented, so we can focus on changing the generator. And we estimate to reduce the generation time down to 15 seconds because we will only generate one model instead of 20 models at the same time. So to sum up, we have decreased the generation time so far from around 20 minutes to 90 seconds. And we think it's possible to reach 15 seconds. And we did some smaller changes, which I also don't explain today, which saved us a lot of time. But it's really important to also think about the generator design right from the beginning and to keep in mind that user models are growing. For instance, last year, a growing user model generation time increased by around 1 minute per month because the user model was growing and the generator was growing. And I would argue that MPS generators are not slow per se, just about the implementation. Okay, I'm done.
So how big are your models?
Sorry?
How big are your models? So how big is the input model and
Yeah.
how many C files or root nodes do you generate?
I should have removed this slide. I removed the slide because I thought I don't have time to explain it. So if I go back to the beginning, so the first slide actually. So we have around 1,000 of those groups. And those groups are like objects classes. So we have calculation formulas inside. And we have around 1,500 of those calculation formulas. And think it was something around 250,000 expression nodes. And then we have 1,500 tests and also a lot of input-output nodes. So you can't count all nodes in MPS because MPS would crash then, but I estimate 300 to 500,000 nodes.
Okay. And
so if I do a query in the console and just give me the size of all nodes, then MPS crashes. But
How many C files do you generate?
We generate around 38 C files of size 38 megabyte. So we have around 38 million lines of code generated. But of course, our generator is not optimized for lines of code. So this is probably also something where we can save some time in the future just by optimizing the generator and don't generate boilerplate code. So we generate a lot of if truths. So having conditions in if files on. Yeah.
And do you have a feeling where would be a performance wall? So you mentioned on the last slide that MPS per se is not slow, but
Yeah.
very often we are guilty for the slowness. Do you have a feeling where would be the performance wall?
I don't know, honestly.
And starting, for example, in the CI, the tool that I suppose takes much longer time than the generator per se, right?
Sorry, could you repeat the question?
So if you integrate the generator in a pipeline,
Yes.
a CI pipeline, you first need to start the CI, the tool run, and then run the generator.
Yes.
I think started and loading the project is longer.
Yes. Yeah, starting headless MPS
Yes.
takes around 1 minute on CI/CD, I guess. Maybe 2 minutes.
Okay.
Okay, this is our last question because we need to go for the next presentation. You mentioned that you are trying to optimize your generator. So I noticed that you are used CPU to computation. Have you already considered also the GPU?
No, but could be a good option, especially now where we know that we can execute root nodes or transform root nodes multi-threaded.
Yeah, exactly.
Yeah. Has it already been implemented, Marcus? No, okay. I'm curious, is there any library to do that? Oh. Ah.
Okay, I'll use an opportunity to not to ask a question, but this kind of presentation has to be the FAQ for when you face and have troubles with slowness of your generator, because all the steps is the way to make your generator fast. There is also few comments I can make on slides, but if we don't have time, just stop me and I'll tell you a bit more about some features that you can use to. But basically, these are the steps. So every time you think it's slow, just do these steps. It will be fast.
Thank you.